Hi everybody, my name's Tom. I'm studying for an MSc in Renewable Energy in the built environment, and I thought I'd put my presentations online so you guys can see it. I think they're quite interesting. So this is the first presentation. It lasts about 10 minutes. I'm going to talk to you about hydrogen, and we think it's quite a benign gas, but can we consider it a greenhouse gas? Does it have an effect on our environment? Okay, we're going to talk to you. I'm going to start about just talking about common greenhouse gases that we all know. Then we'll talk about the effect that hydrogen has on our atmosphere. Later we'll come on to discuss if hydrogen can be given a global warming potential, a GWP. And we'll talk about our current hydrogen emissions, future hydrogen emissions, then we'll come to a conclusion. Okay, so let's have a look at the common greenhouse gases I'm going to discuss. CO2, that's our favourite, that's the one we all know. This has a 20-year GWP of 1. CO2 is a base case, so obviously everything else is reference against CO2. Now, I'm going to talk about methane later on in this presentation, so I think it's good to have a look at methane. Methane's a really strong greenhouse gas. Look at that, 56 times the strength of CO2. And methane emissions are really important. We're going to look at the hole in the ozone layer as well, so I think it's interesting to look at CFCs. These are HCFCs, so actually what we've used to change, gone to change after changing from CFCs. Now, these are really interesting to look at because they have a huge DWP. Their effect on climate forcing is ridiculously large. So this is the question really, does hydrogen belong in this list? Can we consider hydrogen to be a greenhouse gas? Okay, so it's best to look at what happens when hydrogen is released and how it travels through the atmosphere. So when hydrogen is released, it has very low density compared to air. So when it escapes or is emitted, it's only going to go one direction. It goes straight up, go through the troposphere, past the tropopause, into the stratosphere. Now it has chemical reactions along this way, but most of them will be in the stratosphere, which is because that's where it reaches equilibrium, and they'll stay there. Okay, so what happens in the troposphere? Well, hydrogen reacts with hydroxyl radicals and produces water vapour, using this equation here. Hydroxyl radicals are really important for our atmosphere though. They're the main atmospheric sink of methane, using this equation we have at the bottom. So it's important if you see that if all the hydroxyl radicals are scavenged by large emissions of hydrogen, we're going to see longer methane lifetimes, because this is the main thing that breaks up methane in our atmosphere. We've seen before that methane is a very strong greenhouse gas, so I think this is something significant, something we have to look at. Okay, and now it's gone through the troposphere and it reaches the tropopause. Now, the tropopause is an area of very low temperature, minus 60 degrees, and it basically acts as a barrier to freeze out water between the troposphere and the stratosphere. It means that water vapour can't really travel between the two. It does a bit with really bad storms and things, but usually means that the stratosphere is very dry. And if water vapour does get into the stratosphere, it's hard for it to leave, for it to fall down because of the tropopause kind of blocking it again. It's quite important to think that the stratosphere is dry. We should probably keep it a very dry part of our atmosphere. So the hydrogen isn't impeded by the troposphere as we discussed, and it goes straight into the stratosphere. But we've seen a chemical equation that happens before with the hydroxyl radicals. Hydrogen creates water vapour, the same as down in the troposphere. Now, as I said, it's probably not best to make a very dry part of our atmosphere very wet. Now, the water vapour leads to cooling in the stratosphere, creating what's called polar stratospheric clouds, and they're also called noctilucent clouds. And the water vapour, the cooling doesn't carry on down to our troposphere. It actually creates warming. And a 1% increase in water vapour leads to a 40% increase in the climate forcing of CO2. So having water vapour so high up in our atmosphere is really not good for climate change. It's going to cause warming of the surface of the Earth. So what do polar stratospheric clouds do? They work as an activation point for rapid heterogeneous chlorine activations. A bit of a mouthful, but it basically means that it converts more benign chlorine compounds into chlorine on its own. You can see here the hydrogen. There we go. Has made the water vapour. Usually this is little droplets or little ice droplets, and the chlorine compound will kind of sit on it, coalesce on it. But when the sunlight comes in, this is the HV, this is the E equals HF, this is the energy of the sunlight effectively. This kind of splits it, and then we have chlorine on its own, which is quite worrying. Now this creates spring ozone layer holes due to this chemical reaction here. I think it's not quite. And this is, again, you can see the effect of the sun. But this happens most at cold temperatures. This happens a lot faster. This mainly happens in the spring because you have the leftover cold temperature from the winter and then the increased sunlight from the spring. This is, you can see we have chlorine at the start and chlorine at the end, so this is a vicious cycle. This will continue. This is how CFCs break up the atmosphere. This is really not good. This is a very, very bad thing to see. Okay, so can we give hydrogen a global warming potential? Well, we know why it's caused. It's caused by the increased methane lifetimes and the stratospheric water vapour increases, increasing the effect of climate forcing on our atmosphere. And Derwin et al. In 2006 modelled large emissions of hydrogen. They came out of an indirect GWP of 5.8. So, how much hydrogen are we emitting at the moment? What are our current emissions? Currently see this, we see 15 plus or minus 10 teragrams per year. You can see the huge range of error. This is mainly because of where the hydrogen emissions come from. They come from incomplete combustion, biomass, and in cars and diesel engines and things like that. And this is one of the reasons for the large error rate. We don't exactly know how much biomass is burnt in the world. We don't know how it's burnt. Is it burnt on open fires or in ovens and things like that? And in the internal combustion engines, we don't explicitly measure for hydrogen, but we can measure for carbon monoxide, and from that we can make an estimate of the hydrogen, the incomplete combustion. So what about our future emissions? What's going to happen? Are we going to see huge plumes of hydrogen like here in the Eagle Nebula? It's very beautiful, but I think it would be quite devastating for our atmosphere. Well, if we change to electric cars, we'll see a decrease because we don't have the internal combustion engines that are creating the hydrogen. And if we change the way we burn biomass, we can see a decrease or an increase. If we can burn in stoves where there's more complete combustion, the hydrogen emissions will go down. This will also be great for surface level air quality, especially in developing countries. Biomass burning in open fires can cause very bad health problems, so that would be a good thing. But the main kind of point of this talk, as you can see from the background, is what would happen in a hydrogen economy. Would we see huge emissions of hydrogen as hydrogen is being used throughout the world? And hydrogen is very difficult to store, so we would see quite large emissions. But a paper by Kalele, Jacobson and Golden recommended that if we can keep leakage rates to less than 3%, even for a large-scale global hydrogen economy, our emission rates will be similar to what we're seeing today. So not great, but it's okay. Can we get 3%? I mean, is this seen as obtainable? Well, here are three main papers on the effect of hydrogen on our atmosphere, and they don't really know. I mean, look at this. Look at the wide ranges. We've got 0.3% down at the bottom and then 20% up at the top. So it's very difficult to predict. We're not entirely sure what our emissions will be, or even if we will have a hydrogen economy. Okay, so as we don't know, we can kind of make a guess to see what effects we'll have on the emissions, on our rates of emission, how we will stop it. A reason to look at storage of any fuel is it safe? And if we have leakages, will that be dangerous? We know that if it is dangerous to have leakages, we'll design in storage medias that stop hydrogen leaking. Hydrogen is very difficult to store and it's highly flammable. And I think we all know about poor old Hindenburg. That's what most people think when they see hydrogen, that it is a very dangerous fuel. But really, with storage, it's not considered too much of a danger. We have hydrogen here on the left. You can see because the density is so low, it just escapes, goes right up into the atmosphere. So small amounts of leakages really aren't a danger problem because it won't coalesce together and it won't ignite. This is compared to methane, which is still a light gas, but you can see it pools together. We have more concentrations, more risk of ignition, especially compared to petrol, where it stays at ground level. Leakage of hydrogen. I mean, hydrogen is highly flammable, but it's not considered dangerous. So our leakage rates will probably be governed by economic considerations, because there's not too much danger to think about. Here we go. That's what we're saying. This could be a problem. It's very expensive to create the seals and properly contain hydrogen. That's when Rowan warned that higher emission rates might be economically acceptable, especially if you use current pipelines and just try to change them. He said that leakage rates of up to 10 or 15% might be the economically advantageous, because it costs so much to put all the seals in and retrofit it. So in the future we might need legislation to keep our emission rates at less than 3%. Okay, so what are our conclusions? What have we learned today? We've learned that hydrogen emissions lead to higher methane lifetimes and stratospheric water vapour. This leads to indirect GWP of 5.8. So rather than being the benign gas we kind of think it is a greenhouse gas. If it emits, it has an effect on our atmosphere. Causes spring ozone holes, and we really need to look at limiting future emissions. If we're going to have a large-scale hydrogen economy, we really need to cut our emissions down. And this is the slide we had at the start, except hydrogen at the bottom, with our indirect GWP of 5.8. Okay, thanks very much for listening, guys. I'll try and put my essay abstracts on and my presentations on and anything interesting I find on the course, so hopefully you'll find it interesting too.